tree-based method is good for understanding feature importance. We can easily test which input predictor is important to decide our decision. Even for random forest, we can easily understand which predictor is good, which predictor is useless to decide our decision. How can we measure the feature importance? There are many ways, but I want to introduce this very simple approach. First, just train your model, your tree model. And second, pick an input predictor. Pick an input predictor you want to test. And then randomly permute the predictors values, and then check the decrease of your performance. So if the decrease in accuracy is very high, then this means the selected input predictor is very important to decide your output. But if the decrease is very minor, then this means the selected input predictor is very useless. It's kind of dummy variable. Okay. Next one, I will introduce another very important concept for statistical machine learning called boosting. It is very important to understand boosting concept because this is very powerful and many winning algorithms utilize this boosting idea. Okay, so you can leverage the boosting concept to have very nice performance. If you try some challenge or if you do some your own project, I strongly recommend to try boosting method. Okay. So to understand boosting algorithm, I want to start with gradient descent. When you optimize a function, gradient descent algorithm is very powerful algorithm. What is gradient descent algorithm? When you want to optimize fx, and if you want to find the solution of this optimization problem, first start from a random point x0 and then iteratively update your x point using the gradient at the current point with some step size gamma. Usually this gamma is some small constant value. Okay, then because the gradient is the slope of your tangent line, so when you move negative direction of your gradient vector, then this can guarantee some negative drift of your utility function value when gamma is sufficiently small. So when you take very tiny step here, you can always guarantee that the negative gradient direction can decrease your function value. So because each update can decrease the function value every time after sufficient number of iteration or after infinite number of iteration, you can expect xt in the end can converge to some optimal point. If this non-convex problem and needs some local optima, you can expect. So this is gradient descent algorithm, and this is very, very powerful for function optimizations. Almost every modern machine learning technique utilize this gradient descent algorithm to find out best parameters. Okay, like this, the boosting method is very simple. At the beginning, b is 1 and f hat the result function or your decision function is 0. So this is kind of initial point, random initial point. And so in this case, you have n number of data points. Let's say this is xi, yi, and I is from 1 to n. And using this training data point, you train your model FFB. For the boosting method, we usually use very, very simple model like depth 1 tree using only one internal node, 2 terminal node, or 2 internal node, 3 terminal node. So very, very tiny tree we use for boosting method. So anyway, so using the very simple tree model, you train your decision function FFB so that this FFB can predict yi very well. But because we use very tiny, very simple model, the quality of your output may be very bad at the beginning, okay, at the first round of your boosting process. So from the FFB, you update your decision function f hat like this. F hat x plus lambda f hat bx. So this is kind of gradient and this is kind of step function. So at each time, you find out a simple function that roughly predict your output yi. So this f hat b function indicates some kind of good direction, your decision, and using this direction, you can decrease the RSS value. If the task is classification task, then you can expect less misclassification. So this is kind of gradient step. And especially when lambda is very tiny, you can always decrease RSS value or error rate using this process. Since f hat is updated, you change your data point in this way. So which means you just record the remaining portion you have to fit. Because your function f hat moved toward f hat b direction this amount, your label yi already predicted this amount. And from the next iteration, you just need to fill the gap, the residual part, yi minus lambda times f hat b xi. So using this updated data point, you go back to this step, train f hat b again. So here b is counter of your simple trees. You update you train new decision tree, very simple decision tree, and move your total decision function to the newly found simple decision tree direction with a very tiny step size. very tiny amount, and update yi again. Train new tree, update to your function, update to your upper label, train new model, update to your function, update to your upper label. When you iteratively perform this simple process like a gradient descent rule, after sufficient number of time, you can expect very, very accurate function. And very importantly, when lambda is very small, the result ff function becomes kind of smooth because the size of jump for its discrete boundaries becomes very tiny, and it looks like a very smooth continuous function, right? So this is, let's say this is original tree function looks like. But when you set lambda is very tiny, then function becomes very, having very tiny step shape. So it looks like a continuous smooth function. And it becomes very nice, very natural, and you can expect very nice accuracy. So this is boosting idea. And this simple trick can make your tree-based method outperform all the existing algorithm, and this make your algorithm win many Kaggle data challenges.